you take cells that are not primed for this, like your liver cells, which don't have as much mechanical activation and are not as mechanically responsive, then they don't really behave the same way. So what we want to do is make these little building blocks, assemble them together in a controlled way, and generate larger tissue complexity. So this assembly process is actually not trivial, because self-assembly at the molecular scale is, of course, understood, and this is how we're actually built and most biological systems are developed. But at the micro scale, the same forces that are affecting at the molecular scale are simply not strong enough to be able to induce self-assembly. So we've been looking at other kinds of ways of inducing this assembly process. So, for example, using surface tension to induce the assembly. So if you have, let's say, simple things like oil and water, you know that they phase separate, and if you have a drop of water and oil, it tries to minimize this interaction and form a spherical droplet. Well, if you have, like now, gels that have a particular kind of shape, these gels can come together, but because they have a particular shape, then they can actually start forming more organized assemblies that aim to do the same thing, to minimize their interaction with the oil phase. So here you can see that if you have a lot of excess liquid, you still get a lot of droplet-like structures, but as you remove this excess liquid, you start getting packed structures that these gels can actually come together and pack in an organized way. So the good thing about things like oil and water is that people actually use them to make emulsions of cells inside gels, so it's a very robust system, and it's fairly benign to cells. But the process that I showed you is limited in many ways. So we've been actually trying to make this more directed by using techniques like controlling the shape of these particles, make lock and key structures so that as they start assembling, they're more organized assembly, or actually change the system. So we've been interested in using surface tension at a liquid-air interface also to assemble things. So here's an example where you can do that. If you have an object at the liquid-air interface, it actually bends a meniscus. It creates a meniscus, and depending on the shape of the meniscus, whether it goes down or up, it actually creates forces to induce assembly as well. So you can get patterned and organized structure. We've been using this for tissue engineering, to basically similar kind of process where we put these building blocks and then they start assembling together spontaneously and getting more larger complex structures. And this is, you can't see it well, but the idea here is that you can start with individual building blocks and put together to make some kind of assembled structures, and then put those assembled structures together and get more and more complex hierarchical structures. So you can actually get hierarchical structures that actually have a repeating pattern, similar to what tissues are. So we've been developing ways of putting this in 3D as well. So you can actually, this liquid-air interface is a two-dimensional process, but you can make it 3D by creating a template where you can wrap these little gels around. So here you can actually get a template that is wetting to the liquid. So you can have this template, you can put this liquid plus your gel particles on the template where they can start assembling. And once they're assembled, you can remove the template and get your three-dimensional structure. And you can do this to generate a variety of different kinds of shapes. You can do it having multiple layers of these assembled layers, and of course you can use your lock and key processes. In the last 3 to 4 minutes, I want to talk about some of our attempts at creating tissue vasculature using these microfabrication techniques. Well, here we've been interested in using basically microfluidics as a way of creating your tissue vascularization. So one of the things with MEMS-based technologies is that you can actually draw where you want your channels to be. And whether you want them bifurcating and you want to make it small capillaries, you can actually draw it. And you have the capability to actually generate and fabricate these. So there's been attempts of doing this before, using a lot of materials that were not very good for generating tissues, and the approaches here have resulted typically in things that look like devices and not really tissue-like structures. So we've been taking similar kind of approaches, but with hydrogels, where we can take these basically liquid gels, then cross-link them to make them more robust, and we can actually engineer these micro channels inside them. So the process here is not very clear, but it's a molding approach where we can take these gels and create channels inside the gels and have cells. So imagine you have your jello filled with cells, and then you can put channels in there, so you can create some kind of blood vessel-like structure. So the process here is very scalable, and the sizes are also very controllable, from hundreds of micrometers down to sub-micrometer length scales, much beyond the resolution that you would need. And what's interesting about these hydrogel channels is that they behave in a very particular way. So you can flow liquids through the channel, but since the walls are also 90 to 95% water, then the liquid can actually start diffusing in a radial direction. So here, if you flow a dye through this channel, initially it's all restricted in the channel, but if you cut a cross section after a certain time and look at it, you start seeing the dye is penetrating all over. And this can start mimicking more tissue-like behavior. So if you put cells in these materials, then you start seeing a similar kind of response as tissues would. So here you have cells. Initially they're all happy, as shown by this green color, but after a few days you see a ring of viable cells adjacent to the channel where the oxygen and nutrients are at their highest concentrations. And what happens is that as you go further and further, then there's more depletion of these components, and you get more and more of these dead and red cells here. So, and of course what we're trying to do is put blood vessel cells on these channels to make them endothelialized. So here's some example. You can create these bifurcating channels and try to start putting in endothelial cells in them. These are very early experiments, but that's where the direction is heading. So you can actually start creating an artificial vascular network. So that's generally the gist of it. I wanted to give you a sense of some of the work in this area, and I think it's a very broad and open field when it comes to applying these microfabricated systems for different regenerative medicine applications. And you can see that there's a lot of room about applying them to generating tissues or understanding biology, but there's also a lot of experiments that we and other people are doing in trying to create high throughput experimentation systems and be able to use them for drug discovery applications and minimize the use of animal use, etc. So I've had lots of great people in Boston who've been helping me with this. NIH is in the US is where the majority of the money comes from, so they've been nice to me, and a lot of great collaborators, and a lot of great people who I know here who've really they've been wonderful colleagues over the years. Actually, Ahmad Morsi invited me, so I owe him this wonderful trip. And a lot of other good people who I've met over the next few days, and I hope to meet many other good people over the next couple of days. And if you are not been to Boston, then I definitely invite everyone to come over. This is how Boston is on a good day, which happens about 10 to 15% of days. And this is how it is on a typical day, which is 85 to 90% of the day. But it's very nice, a very great scientific environment, and everyone is welcome to come. I put my contact information here because I aim to get some emails and reply to them. So thank you very much. If there's any questions, I'd be happy to answer in the next 3 to 4 minutes before we start the next speaker. I know it was crystal clear, so. Yes?
Do you think that the program for the stem cell is inside the cell or inside it or inside from outside?
Sure. So excellent question. So about whether what really regulates it is within the cell or external. I think it's really a combination of both. There's a lot of things that happens automatically. Like basically, once cells are primed to do something and they're conditioned to behave a certain way, then a lot of signal pathways happen automatically. But what is less kind of what really requires the outside control is sometimes what instigates the initial patterns, initial behaviors to occur. So and this is true because we know every cell every cell has all the genetic program to become any other cell type. So that's why there's induced pluripotent cells that you can take cells from your skin and make embryonic cells. So when you have a very primitive cell, it really can become lots of different things. And the way it decides, at least the initial step, is by what it sees from its surroundings. And then once it takes the first step, then a lot of times then it can go the rest of the journey. So, and because it's already programmed to do that. But what we're trying to do is give it the initial signal, and then hopefully, you know, if it needs some other direction down the road, give it to them. But the cells have a lot of capability within them. And they're really, you know, there's a good saying that says that the best tissue engineer is actually the cell, and, you know, not the people who say we're doing tissue engineering. So.
Okay.
Yes.
Thank you very much indeed for your presentation. I'm trying really to think of how can your field be related to the diseases like cancer, like the immune system, dealing with the immune system. How can you see this?
Sure. So excellent question. So regarding the immune system, because there's actually a very interesting field where people are starting to pick up these techniques. So because contact and interaction between immune cells is so important, if you have an in vitro system, then a lot of times people want to control how this environment occurs. So there's been some very interesting work where people are trying to look at you know, immune cells interacting in a dish, where they can literally pattern the cells and control how they come together and what happens subsequently. So that's the in vitro development and understanding of the immune system is one way. Regarding cancer, it's also an interesting kind of direction, because one of the things that people are trying to do is to try to make predictive drugs, like models that are predictive. So people have been treating cancer in mice for 20, 30 years now. And the reason they still can't treat humans is that because mice are not humans. So if we can actually start developing human tissue models that have the same kind of behavior as a human cancer does, then you can have more predictive response of your drug or your drug delivery system, etc. So I think there's room in that area. The other thing that I didn't talk about too much is there's been a lot of room, a lot of development in actually trying to make micro and nanoparticles using different shapes and different kind of materials. And using the same kind of techniques that I mentioned here, people are starting to develop nanoparticles that have a particular kind of shape, and it actually changes its distribution and how it actually pharmacologically is active. So there's the whole separate way about how shape of these structures can actually be used for therapeutics, which I didn't talk about as well. So in the interest of time, actually it's good if we move on. So I asked the next speaker to come up here.